I would like to welcome our keynote speaker, Dr. Daniel Colbourne. Dr. Daniel Colbourne is an expert in natural refrigerants, and he works on behalf of various organizations, companies, international standardization committees, and he is a member of the Institute of Refrigeration Technical Committee and director at Re-Phridge. And today, we are very happy to have him here and to listen to his keynote on building a better future the natural way. Welcome, Daniel.
Thank you very much, Ulrika, for the introduction. Let me put my presentation up.
The floor is yours, Daniel.
Thank you. And thank you also to GIZ and the Ministry as well for a kind invitation to come and speak this morning. Okay. My presentation, it has a very broad title, Building a Better Future the Natural Way. To reiterate a few points that were just recently mentioned, the impact of building indoor climate control, heating and cooling around the world is quite considerable. Building heating and cooling accounts for about 30% of global energy use, as was previously mentioned. This corresponds to around 5 to 10 gigatons of CO2 equivalent, depending on which source you look at. About 8% of the direct emissions are due to refrigerants and combustion products. 18% of the emissions are indirect emissions or due to electricity consumption. Each year, the energy cooling for building increases by around 5% per year. That was another upwards trend that was just mentioned. Air conditioning accounts for about 7% of global electricity use and around 3% of the CO2 equivalent emissions. Of course, there's gas and oil heating, which also has a large contribution, which is approximately 8% of emissions. There's all sorts of numbers floating around, but the main point is that we all understand that it's a significant contribution to climate change. So it's important that we do as much as we can to minimize those emissions. Of course, one option is to stop using indoor climate control, but of course, society needs to avoid the extreme temperatures, both high and low temperatures, not only to exist, but we require fairly comfortable conditions to function effectively, do our jobs, enjoy our existence. Furthermore, the use of air conditioning or climate control avoids premature deaths. Some estimates say up to around 200,000 fatalities per year are avoided. Of course, a greater number of fatalities are avoided by means of building heating. So for our well-being, it is an essential function. But on the other hand, as was mentioned on numerous occasions, and I would then say it's blatantly obvious that this indoor climate control is causing or contributing to severe climate change, and so it must be done in a sustainable manner as possible. We've had mechanical refrigeration systems for something like 100 years, but of course society existed for millennia before that and functioned quite nicely in extreme climates. And of course, if we look back, we find archaeological evidence of this. There's some sort of common photographs here of the building technologies that enable a more comfortable indoor climate to be achieved without the use of electricity, without the use of mechanical refrigeration, without the use of climate damaging refrigerants, just mainly through the design of the building. So this is perhaps the emphasis of the topic that I will discuss here on. There's all sorts of ways of cooling and heating different buildings, or living spaces, working spaces, and so forth. And in this slide, I have a hierarchy, or what I consider to be a hierarchy in terms of minimal climate impact. So right at the bottom, we have what I call other. So these are obviously the fossil-driven technologies, so direct heating and so forth. It could also be cooling through heat-driven cycles, heat-driven refrigeration cycles. Next up is conventional vapor compression, mechanical refrigeration driven by electrical power. Most common today, sadly, are the systems that use fluorinated refrigerants. But as we are all aware, the use of natural refrigerants is becoming more and more prevalent. The next level up is what I've called partially free climate control. So it generally needs a little bit of energy to drive it, but the amount of cooling is potentially, or can be, very significant for a small amount of energy input. So that includes ground, water source, thermal exchange. So that, when I say thermal exchange, that refers to both cooling and heating. Desiccant cooling, where you remove the moisture from the air, and evaporative cooling, where you use the evaporation of moisture to provide the cooling effect. And then at the top of this hierarchy is the passive building climate control methods, which I'm sure most people are familiar with. So natural ventilation, thermal storage, green roofs, which was mentioned earlier, and so forth. So generally further up this list, up this hierarchy, the operational impact is minimal. But of course, there are other implications that affect our choice of climate control technology, and that, of course, is money. I have a little diagram on the left here. There's always a balance in a lot of cases between minimizing the emissions and what the cost implications are. So a lot of these technologies that I've mentioned in this hierarchy, they can be applied very nicely, but in a lot of cases, in a lot of situations, the investment may be higher. But it's not always the case. Oops, excuse me. Before I go on, it's important to clarify what we mean by human comfort. Well, human comfort is basically achieving a set of conditions within a very narrow band. So obviously temperature, we like a temperature of somewhere between 20 and 25 degrees C, although we can be happy in a slightly wider band than that. Humidity also needs to be within a fairly narrow bands, between 40 and 60, but we can also tolerate something slightly wider. There's other than temperature and humidity, there's other local conditions that can also influence our level of comfort. So, for example, direct sunlight, air movement, a nice little breeze in the background improves our sense of comfort. Thermal radiation, whether it's coming in, for example, from the sun or going out towards a cooler surface, that can also affect our sense of comfort. But of course, a whopping great big delicious ice cream also helps. increase our sense of comfort as well. So it's important that when we consider these different technologies, we can achieve some level of temperature, humidity, and other control that fits nicely within our comfort range. So what are these different technologies that that can be applied to achieve free or fairly free levels of climate control? I think most of you will be familiar with these. There's geothermal cooling. So the ground is generally a few meters below, it's generally around 10 degrees Celsius, and that cold can be used to remove the heat from a flow of water, which can then be pumped around a building to provide cooling. On the other hand, we can also consider geothermal heating. So we dig down a little bit further, a few hundred meters, and then we can achieve quite a warm or quite a high temperature. So again, pumping water down there and passing that warm water around the building to provide heating. Got evaporative cooling, so that's using the evaporation of water to cool the air. Thermal convection, where hot surfaces heat up the air beside it. The lower density gas, the lower density air flows upwards, and that induces in cooler air. Then we've got what, I call it the real greenhouse effect. So that is, like your greenhouse, using glass or transparent surfaces to allow the sun's radiation to come in but not to go out again. And that can provide quite a significant warming effect. Then on the right, we've got thermal storage, which again doesn't provide cooling or heating directly, but it provides a sort of averaging effect. So it can provide cooling on warm days and heating on or warm periods of the day and cooling on cold or on other periods of the day. And then again, a combination of these various technologies, we have green roofs. And green roofs rely on a number of these different features. So there's an effect from evaporative cooling, the moist soil, reflecting the thermal radiation, and the sheer mass of it. So there's some sort of thermal storage there as well. So there's all sorts of different natural phenomena that enable free climate control. And next to some of these, I've indicated the amount of temperature change that can be achieved through these methods. And I think that's important, particularly with respect to the next slide, which is considering where people live around the globe and what the local climate is. So if people are living in extremely hot regions or extremely cold regions, then you need to use some of these natural or free-ish cooling technologies that will suit the local temperature differences, or that would suit the local climate in order to achieve a temperature change towards what we find comfortable. Of course, if we look at all of these technologies or these free cooling technologies, there are, of course, cost implications there. And generally, it requires planning and thought right from the beginning of the construction process. A lot of these won't be applicable to a concrete block of flats that's already been built. They need to be integrated into the building. And obviously, modifying existing buildings can be quite considerably expensive and generally prohibitive in a lot of cases. It's important. So it's important to consider these features, these technologies right from the outset. But of course, 90% of the living spaces are already built. So somehow we need to acknowledge that some mechanical cooling is required. And so vapor compression systems are always going to be needed as long as costs are involved with implementing heating and cooling into building spaces. Excuse me. If we have a refrigeration system within the air conditioner or the heat pump, for example, we want to achieve as higher efficiency as possible, of course, but that in itself has cost implications. On the right-hand side, we have the classic pressure enthalpy diagram, which shows the refrigeration cycle in green. And the question is what can we do to this cycle to improve the level of efficiency? We have an outdoor air temperature and an indoor air temperature that we want to achieve. So what do we need to do on our refrigeration system to achieve that temperature with as high a level of efficiency as possible? Well, on one hand, we want to reduce these temperature differences between the refrigerants and the outside air. And we also want to reduce the amount of power used by the compression process. The conventional way of reducing those temperature differences is by having a larger heat exchanger. Now, in the diagram on the left-hand side, the blue line shows the coefficient of performance, the cycle efficiency. So if we start off with a typical temperature difference of, say, 20 degrees, we might achieve a cycle coefficient of performance of around 5, which is pretty good across the products that are available. But actually, if we reduce that temperature difference more and more and more, we can increase the cycle efficiency quite considerably, up to a value of about 25. And that sounds very attractive. But of course, to do that, we need to have a much larger heat exchanger, and much larger heat exchanger doesn't increase linearly with the reduction in temperature difference. It's sort of almost exponential. And so you can see here on this orange line, the increase in heat exchanger size. So if you want to achieve a COP of around 25, you need to increase your heat exchanger size by something like 20 times. And of course, if you've got a living space with a heat exchanger that's 20 odd times the size of the one that's already there, there's not going to be much space to live in. And again, having a huge metal heat exchanger has cost implications as well. So of course, by considering all these different approaches, there are always cost implications to address. How about energy consumption? We can reduce the amount of energy we expend on our refrigeration system by reducing the heat load. In our living space or working space, there's all sorts of different heat loads, and which are generally heat transfer from the surroundings and also heat generation from the items inside, whether they're machinery like computers, also from people, also infiltration or exfiltration of air from the surroundings. So all of these things contribute to the heat load. So it's possible to have better insulation, reduce the amount of infiltration from the outside and so forth, reduce the amount of windows. But of course, this in itself can also impact, at some point, it impacts on the level of comfort. So it's very difficult to achieve negligible energy consumption with the refrigeration system. Of course, there's other behavioral aspects, and this is probably one aspect where we can make a significant impact. For instance, rather than setting the air conditioner at 16 degrees and putting thick winter jackets on, we can set a more comfortable temperature and not have not have to compensate. Keeping doors of air-conditioned spaces closed, switching off air conditioning for spaces that are empty or don't need to be cooled or heated. Another issue is distribution of thermal sources. If you look into a household or a working building, there's all sorts of different things that produce heat or use heat, and also produce cold, or you can utilize cold. But everything today is generally separate. Nothing is combined. But of course, when you carry out an analysis on this, you can find that utilizing heat or thermal energy from one for the input of another item can be extremely useful and minimize energy consumption. So what is the answer? It is to combine the construction of buildings along with these various free or free-ish cooling technologies and features to both minimize the amount of heating and cooling that's required, achieve a good level of cooling, and minimize emissions. Related to this is the topic of refrigerant use and natural refrigerant use, where we find in almost all types of systems and applications, we can use natural refrigerants quite widely. There are two sectors, two types of equipment, multi-split or VRF type systems and ducted systems, where we can use natural refrigerants, but unfortunately, the use of, or the requirements within safety standards have obstructed their use in many cases. So it's very important that we address the requirements within some of these safety standards to try to open up all of these different applications and types of systems so that natural refrigerants can be used universally. So thank you for your attention. I just leave you with a few final thoughts. As we all know, across all sectors, emissions of CO2 and other warming gases is not easy. It's a real challenge. The climate control sector requires quite substantive changes, and a lot of these are somehow societal or psychological. We need to be able to do broader thinking. People need to be able to tackle different technologies and combinations of different technologies. We need to be able to integrate the building design and the building construction with handling thermal energy flows. And we also need to address the legislative framework in some way. People won't do anything if it costs them something. So we need to have legislation to direct all of these stakeholders in the right direction, and that includes addressing safety standards to enable a broad application of these natural technologies. So thank you very much indeed for your attention, and I hope it provided a good perspective for the forthcoming presentations. Hopefully from the next presentations you will get a better insight on the technologies to reduce emissions, and where they will dig into other alternatives and pay attention to more detail. So thank you very much for your attention.
Thank you very much, Dr. Daniel Colbourne. And you can see already some reactions coming from our participants. So dear participants, please applaud, send some hearts, show some affection for this presentation. Thank you very, very much.